All right, now that we have had the words of wisdom saying that recording is progress, it's my pleasure to welcome you all to our second graduate student visitor talk this week. So if you missed the first one from Dr. Kim, please go to YouTube in a couple of weeks or whatever. Just watch this video and watch that one as well. But today, it is my pleasure to introduce Lucía Ferrari, who is here from the Astrophysics Institute in La Plata, Argentina. And so she will be talking about supernovae and their progenitors from late emission. And you are also a PhD candidate right now. So okay. And so take it away.
Okay, thank you very much. Thanks for the introduction. Also, I wanted to thank the Gemini Observatory for letting us being here. This week has been amazing. Lots of new information and new things to learn. So thank you very much. I'm looking forward to go up to the summit tomorrow. So that's why I'm drinking lots of water. So, well, yeah, I'll start. As Zach said, I'm Lucía Ferrari. I'm doing my PhD in Argentina. Gaston Folatelli is my supervisor, and we work together with Dr. Gaston with Hanin Jokunkarajärti, who is working at the University of Turku in Finland. So, well, my PhD thesis is about the supernovae and their progenitors from the late emission. So I'm going to start with a short introduction on what supernovae are. So you may all be familiar with this, but still, the supernovae are extremely luminous and energetic events in the universe. They can come from two different physical processes. One of them is the collapse and explosion of massive stars at the end of their evolution. And the peak luminosities of these objects can range the 10 to the 42 to 10 to the 44 Ergs per second. And they leave behind a compact filament, could be a neutron star or a black hole. And then a long time afterwards, they leave these pretty things that everyone loves, that are the supernova remnants, and well, that's the crab nebula that everybody knows about. The other physical process that can lead to a supernova is the thermonuclear explosion of a white dwarf, accreting material from a binary companion, in a binary system, from a giant companion, and they have relatively uniform peak luminosities around 10 to the 43 Ergs per second. So they are used as cosmological candles to estimate distances to further galaxies. So it is interesting to study supernovae because they are very, very important in the creation and the distribution of the heavy elements that we have in the universe. So their study has implications on stellar evolution, cosmology, the chemical enrichment of the environment, the interstellar medium, among many other things. So supernovae are classified according to the observational properties, mainly classified by the elements in their early spectra. So if the type 1a supernovae correspond to the thermonuclear explosions, and the first big difference is whether the spectra shows hydrogen or not. Then we divide it into type 1 or type 2 supernovae. Then if the spectra shows silicium, then we have the type 1a, which is this thermonuclear explosions. And if not, if they don't have silicium nor hydrogen, we call them as type 1Cs or type 1Bs, depending on the presence of helium. So then if we find hydrogen on the early spectra, we call them of type 2. And if we see hydrogen in emission, we call them as type 2 ends. I will go through this a little bit later. So here is an example of many of different types of supernovae. As you see, it can vary very much the shape of the spectra according to type, although these are like canonical supernovae of each type, and sometimes we find things that are not as easy to classify as this kind of targets. So mainly my thesis is focused on core collapse supernovae, and more specifically on stripped envelope supernovae, which are those that show little or no hydrogen in their spectra. So the thing is that they must have gone through important mass loss processes to lose their hydrogen and sometimes also their helium-rich envelope. So these are the types compared to the plot before. So I mainly work with type 2Bs, type 1B, and type 1C supernovae. And the processes involved in this mass loss is a matter of discussion. We have two main hypotheses. One of them is that the star loses its envelope through stellar winds. So then we must have a very massive progenitor to lose the outer envelope. And it could also happen that it is the envelope is removed through binary interaction. Here is an example of the evolution of a type 2B supernova, the 11BH, from the 10 days previous to its peak light until the nebular phase, which is shown here below. So the main parameter that we want to estimate for the supernovae is the mass, as our goal is to link each type of supernovae and its characteristics in the spectra and the photometry with the progenitor properties. And the main parameter that we want to find is the mass. So there are several methods to do this. The most accurate one is to look for the progenitor in archival images, usually from HST. And you can fit an SED to the archival data. This and then try to estimate which star would produce that SED. The problem with this method is that it is limited to very nearby supernovae, and you have to have actually those the place must have been observed before the supernova will explode. So then another way of estimating the mass is through the hydrodynamical simulations of the light curves. So there are a few codes that produces volumetric light curves depending on the progenitor properties, and then we can construct the volumetric light curves from data estimation. Yeah. And then compare them. And then we have an estimation of the mass as well.
So Lucy, I have a question now that we have an interruption. So the SED fitting, how do you do it? Like, do you need a spectra, or you do it with the different filters that has been?
I have never done it, but what it is done is you measure the flux on different filters of images that have been already before the observation, and you fit an SCD to the different points of the filters that you have. That could be 4 or could be, well, a few more, but not many. I will show an example of this. I'll show an example of this.
Oh, I was wondering because I saw that graphic that has so many points. So this is why I was thinking, wow, that's a lot of data.
No,
Like-
this. You mean this?
Oh, no, the one that you have below, or that's the, oh, that's the light curve, no?
Yes, yes,
Oh,
yes.
sorry.
Okay. This is an example of the light
Yeah, yeah.
curve.
Yeah, I
of
was
the
distracted with that figure. I was thinking.
No, sorry.
Yeah.
This is an example of supernova 13 BBN, in which a work from Bersen et al. 2012 compared the volumetric light curve to different models with different parameters, and then obtained a progenitor mass from there.
And that's a 2B.
That's a
It
1B.
looks like 87A, but it's a 1A. Wait, what is it?
No. 1A, no, it's 30 BBN. Sometimes it has been classified as a 1B and sometimes as a 2B, but mostly as a 1B. And it was a quite a bit peculiar.
Okay.
It's-
I'm probably the only one that cares, so it's okay.
But no one else. No, I won't show anything of 1As. At the very beginning to show that they exist. Yeah. Well, so then another way of estimating the mass is by performing environmental analysis on the stellar populations, where you also study the nearby stellar populations and try to infer the mass of the progenitor star. And the last one, that is the one that I will focus, is the nebular phase, which the nebular phase, I will introduce this in the next slide, but it strongly depends on the progenitor mass and properties. So it begins after 100 or 150 days after the explosion, and it shows the emission coming from the areas that are near to the former stellar nucleus. So it's very interesting to study this because it can give us information about the mass and the structure of the progenitor star, and also by studying the line profiles, we have clues on asymmetries in the explosion. So this is what spectra looks like. This is a figure from paper by Jerkstrand et al., in which he models nebular spectra and compares it with data. So here is the 2004 ET supernova in red, and you see that we have a very low continuum, and then we have the spectrum dominated by strong emission lines that correspond a few of them to forbidden transitions. So that's why it is called a nebula. The presence of hydrogen depends on whether the progenitor had hydrogen in its envelope or not, in principle. We'll go to that too. So this is something that I did for a supernova that I worked with for my undergraduate thesis, but I also I wanted to show it because this is a Gemini spectrum, so it's good to show it here. This is have been like a very famous supernova, the 2016 GKG, because it was the first time that the shock breakout was observed. These few points here are very complicated to observe because you never know when a supernova is going to explode. This was kind of a casualty, and an amateur astronomer was observing a galaxy in Rosario in Argentina, and suddenly he found out that he had a point that was coming brighter and brighter and brighter. So he started taking images. He knew that he was looking at a supernova, so he kept taking images. It was a pity that he didn't do it for a little bit longer. This was very valuable data. And then it was observed by other observatories a day onwards. Well, it was like a very special work for our group back in Argentina. And well, for my undergraduate thesis, I worked with the nebular spectrum together with Hanin Unkarayaki. So then, for the last thing, I wanted to introduce this supernova that it has a very particular story. It's called 2014C, and it's more or less nearby for less than 15 megaparsecs, and it was initially classified as a type 1b, and then it showed signs of interaction with the CSM at later time. So it evolved into a type 2N supernova. So the scenario that could explain this is that we have an H4 supernova or progenitor that is imbedded in a non-standard hydrogen-rich environment. So it is a bridge between the type 1b supernovae and the type 2Ns. And this work by Margutti, well, they explored, they could find a few parameters. The distance to the CSM they found is 6 or 10 to the 16 centimeters. And they proposed that they had like a short Wolf-Rayet phase of a single progenitor star that lasts only for 20 years, and then a very large mass loss rate during the previous red supergiant phase.
So is it only called the 2N because of the interaction with the interstellar medium or a circumstellar medium?
The 2Ns are usually called that way because at the beginning of the at early phases they show intermediate with hydrogen in emission, and
This was a 1B initially.
yes, so it started.
Is it only called a 2N because of the interstellar medium?
Yes, like a transition. It transited.
Circumstellar, but yeah.
Oh, circumstellar,
Yeah.
okay, so, okay,
Sí,
not interstellar,
no,
circumstellar, okay,
circumstellar.
so it is interacting with hydrogen that it produced.
Yes, apparently.
Okay, sometime that it blew off sometime with that.
Yeah, I don't wait for it because not yet. I'll say something about Gemini and then go back to that. So, well, for my PhD, we are doing different things. One of the things that we are doing is that we are constructing a sample of nebular spectra of supernovae. The reason why we are doing this is because recently it has been a few works that analyze large amount of nebular spectra, but usually this kind of works are focused on one single object that show particular particular characteristics. And it is interesting also to have like a wide scope when analyzing various targets at once. So our strategy is we use both Gemini South and Gemini North telescopes in asking for target of opportunity. We use GMOS. Targets are usually fainter than 19 magnitudes. It can be not fainter than 22. And our wavelength range goes from 4,500 to 9,200 angstroms. And they are all low resolution spectra. And we also take images in the G and R band. So here's an example of what we have been taken. This is the image of the 2020 ACAT. And here are some examples of the data that we are acquiring. Our aim is to study line fluxes and Doppler shifts of the emission lines, compare them with canonical and typical other supernovae, and compare our spectra also with model spectra. So this is an example of the fitting of the oxygen doublet and the hydrogen emission of the supernova 2016 GKG, in which we found a multiple component profile. So this is what we are constructing, and now I want to talk about one specific object that we have been working on that, like the 14C supernova, also presented a metamorphosis from the early times to the late times. So it was originally classified as a type 1b, and then around 70 days after the V1 maximum, it started to show signs of interaction with the CSM. So here's the spectrum of the supernova around the maximum light. And here, as you can see, there is no hydrogen absorption there. And this is the H alpha emission. This is compared to a type 2N supernova at later times. And we see that the hydrogen emission is very important. So this work was combined data from several telescopes. We have data from VLT, NOT, NTT, LCOGT, and Subaru. And due to the high cadence of the data, we were able to distinguish the exact moment in which the interaction became at least visible. I'm going to show this later. So previously, a work by Kilpatrick analyzed the progenitor candidate. This is one of the few stripped envelope supernova that had archival images and a progenitor candidate recognized in those images. And then also there have been an analysis of the environment and the progenitor candidate of the progenitor candidate by Sun et al. In 2021. So what we do here is we analyze the interaction signatures on the light curves and the spectra. We give a mass loss rate estimation and estimate the progenitor properties. For the future, we plan to include the optical, near-infrared, and high-resolution spectral analysis, and try to understand in detail which are the effects of the circumstellar interaction with the ejecta of the supernova, and how it affects the nebular spectrum. And recently, it has been approved an HST program to reobserve the site. So we will know if the point source that was found as the progenitor candidate was actually the progenitor. So here's the most interesting part of the spectral series. We have the evolution between 42 and 118 days after the maximum light, and we see how the H-alpha emission appears. This is in comparison with two helium lines compared. This region does not evolve much, and this is affected by the presence of H-alpha. And while we see this hydrogen emission, we also note a break in the light curve, and we note a departure from its normal decay rate at almost similar at a similar phase. This is compared to other typical supernovae, the 11DH and 13 BBI. So, well, these are this is the transition between the early phase and the nebular phase. Then we had spectra in the nebular phase, in which we see that H-alpha has an asymmetric profile and is shifted by a few hundred kilometers per second, and its width is of 2,000 kilometers per second. We see a double peak profile on the oxygen doublet, which also is shifted by 13 kilometers per second and a wide of 20 and 25 kilometers per second. We note also that the calcium triplet is unusually strong. We haven't found a reason for this yet. So if you have any ideas of what could be happening, you're welcome to hear it. So we estimated a few properties for the CSM from the nebular phase. So by adopting maximum ejecta velocity of 10,000 kilometers per second, this is based on our measurements of the velocities on the earliest spectra. We find that the CSM is located between 6.5 and 9.1 and 10 to the 15 centimeters. If the CSM was expelled by stellar winds of 50 to 100 kilometers per second, the mass loss must have occurred up until 20 to 60 years prior to the explosion. So then from the H-alpha luminosity in the nebular phase, we find that the mass loss rate must have been of between 3 and 7, 10 to the minus 5 solar masses per year. And if we consider like a limit velocity for the shock of 2000 kilometers per second, then we end up with an upper limit of for the mass loss rate of 4 to 8, 10 to the minus 3 solar masses per year.
So the 3 to 7 times 10 to the minus 5, that's for the mass loss rate prior to the supernova explosion?
Sorry, I didn't.
The first number, 3 about 7 times 10 to the minus 5, that's the mass loss rate prior to the supernova.
Yes.
And is that upper limit also prior
Yes,
to the
yes,
supernova?
because this takes two different shock velocities. This is like a very limiting situation. So, I mean, the mass loss rate could not be more than this.
Okay.
But it depends on the ejecta velocity. So
That's 2 order of magnitude.
yes,
Upper
yes.
limit 2 order of magnitude.
Yes. This is very unlikely to have this ejecta velocity. We we measured something like this. So yes, it was like not very probable to have this situation. So then going to the progenitor properties, we performed a few methods to infer the progenitor mass. The first one was using the 1D Lagrangian hydrodynamic code from Bersen 2011, which models the volumetric light curve and the photospheric velocity at early times. And the three parameters are the explosion energy, the shakedown mass, the mass of synthesized nickel, and the mixing of the nickel. This energy is deposited at a certain mass coordinate, which is called MCAT, and all the mass inside that MCAT then becomes the compact object. So we find that our best match corresponds to a helium mass between a helium mass star between 3 and 4 solar masses, which is in accordance to a zero-age main sequence mass star of 13 to 15 solar masses. We have also,
Lucia, in the progenitor study, does it look like a yellow supergiant?
it looks like a yellow supergiant.
Okay.
Yes. That's from the SED.
Okay.
It's apparently a yellow hypergiant.
Hypergiant, okay.
Hypergiant is the proposed progenitor. Yeah. Which is a problem because it should have hydrogen. So yeah. Yes, the scenario is still in discussion. So that we tried also with more massive progenitors, but we didn't find a set of parameters that would match both the volumetric light curve and the velocities. So then we move to the analysis of the nebular spectrum, nebular spectra, and we compared the ratio of the oxygen doublet to the calcium doublet, both forbidden. And this ratio have been suggested as an indicator of the progenitor mass. And we compare them with the grid of models published by Besart 2023 for straight envelope supernovae. It was good because he publishes the spectral evolution between 100 and 400 days for a wide range of initial helium masses. Our measurements are in accordance with also relatively low helium masses. And finally, we use the direct measurement of the oxygen doublet flux, which is also is linked to the minimum oxygen mass that we should have to be seeing that be receiving that flux, and we can relate it through oxygen yields in the explosion to the progenitor masses. And this is very this method is very sensitive to the temperature assumption on the material, and also the flux could be contaminated by this CSM interaction. So we don't rely very much on this result. We just use it as an upper limit, and we find that the progenitor is around 15 to 20 solar masses. So, as a comment of the previously published works, Kilpatrick performs this study on the archival images, and he finds no variability in the previous 3-year to 2-year time range before the explosion. So it is not possible that the progenitor was going through strong variability or activity during that time. And it's not conclusive on the progenitor system. And what Sun proposes is that there are two stars in a binary system, and the cool yellow hypergiant dominates the SED, the emission of the SED, and then you have a compact, not so massive progenitor of the supernova.
What is the bluest? Was it 5? Yeah, the bluest filter in from HST.
4, 3.
Okay, so there was no like UV stuff to, yeah, okay.
So, the highlights of our work is that we show this late time interaction for the supernova for the first time, and that we highlight that a progenitor with no hydrogen, as is shown by the early spectra, evolves into a hydrogen-rich supernova at later times. So Kilpatrick suggested 2 progenitor scenario, one massive star that went to a series of eruptions in an LVV phase, or a binary system that led to mass loss episodes 9 years, many years before the core collapse, and soon suggested a hot and compact progenitor in a binary system and the yellow hypergiant companion. Our results would point to a relatively low mass star, so it wouldn't seem like to favor a single star going through a luminous blue variable phase, but still the scenarios are open. So for the last part, I wanted to talk about the supernova 2023 IXF, because this is using GMOS Gemini data, so I wanted to show it, and also because it was work done in collaboration with Jennifer. So I guess that you may all be familiar with this supernova. The 23 IXF exploded last year in May, very close to us.
Back with the bang one, guys.
Oh, that one.
There you
So it's very close, less than megaparsecs away. It's funny because although it's very, very close, it has archival progenitor detected on archival images. And the estimates of the progenitor mass are spans from 8 to 24 solar masses. So I don't know if it's because there are many publications about it or why, but although it's one of the closest ones, it's very, very, it can vary too much what the conclusions are. And it had shown also early interaction with the CSM. So this is a spectrum taken by the program led by Jennifer. in February, I think. So this is a type 2 supernova, and we see hydrogen as we expected. Then the normal emission lines, the oxygen, the calcium. We have this little peak here that we don't know what it is. The calcium triplet. Well, and this is an image taken for my program, and I am waiting for the spectrum from the next spectrum. So if anyone here knows what to do for it.
So Brian, through the band 3 program. To me,
309.
yeah.
And dark time, by the way.
So the study that we performed, we studied its emission lines. We find a general blue shift of the emission lines. Also a two-component profile of the oxygen doublets and of H-alpha. In H-alpha, we see a wide and rest-centered component, and then a blue shifted and intermediate component, and for the oxygen to narrow components, and then the wider ones. So the scenarios that we propose are that we have either two intrinsically different emitting regions at different velocities, or that the material part of it is being slowed down by a pre-existing or with clumpy or asymmetric CSM. And we also estimate the progenitor mass, firstly from direct comparison to models by Jackstrand of type 2 supernovae. And we find that the best match is between for progenitors between 12 and 15 solar masses, which is confirmed when we compare the flux ratios of the oxygen to calcium doublets with those of the model. Then from the direct measurement of the oxygen flux, we find an upper limit between 15 and 17 solar masses, depending on the temperature assumption. So, well, that is it. Thank you.
Any questions?
Could you go back to the explanation for the supernova before IXF?
Yes, sir.
Yes, okay, so a binary system that lived the mass loss episodes years before the supernova, what would cause it to happen and then stop?
Yeah, no, that's the question. What I also don't, I mean, I guess that the envelope, the mass loss should be continue or should occur continuously and fill all the space between the outer layers of the star. And so why we have like an empty or relatively empty, so we don't see the interaction before the like an inner radius of the CSM, when we don't have something like a radiation campus that will, because it's not a super luminous progenitor. Is that is the question that needs to be solved? Yes, yet. Yeah. But if you come up with an idea, no, our idea is to go into binary evolutionary paths to see what could, if there's any way to form a system like this in which you have an hypergiant star that is not the one that explodes.
Yes.
Yeah.
But he obviously thinks that's a plausible.
Yeah.
Kilpatrick, I probably think that's a plausible
I don't know, he doesn't seem too convinced. In the paper, he's like, this could happen, but I don't know. I don't know. Yeah, they also mentioned something about the common envelope evolution that is very hard to model as far as I understand. So they say like here's a lot of work to do, but still we're not able to distinguish what could be happening. Yeah.
So is it mass loss from the hypergiant onto the other companion or just out of the system?
No, the idea would be that the progenitor loses its envelope to the other to the companion and forming a shell or some shape of a CSM, but detached from the location of the progenitor. One of our collaborators was interested in the possibility that the interaction could be happening before we could see it in the spectrum or something, but we don't find any like bluer component or it when we compare the absolute light curves, we don't see any offset to the normal luminosity of this type of supernovae. So it's not it's weird, and it is now usually it is common to they are starting to find with the flash spectroscopy, which is spectroscopy very close to the explosion of the supernova. They are finding that sometimes there is some CSM very close to the supernova, and then they see an emission line at the very beginning in the spectra, and then it fades away, and you have the normal spectrum. So if an interaction was occurring, we should be able to see it. So,
How early was your first spectrum?
very early. I think. I don't want to lie. Maybe 3 days after the discovery.
But one of these or two of these sometimes have like a first peak, right? And then like quick and then another. So
Yeah.
there could be, okay.
Yes. I don't know if this is the case. I don't think so. At least it was not observed.
Yeah, we
The last
have
one we
limits, pretty strict limits on when it exploded, right?
Yes, I don't remember now how far. I think the last non-detection was like 5 days or something before this. Before
So I
the
mean, there
first point.
could have maybe been narrow lines,
Yes.
possibly, but okay.
Yeah, no, but my point is that if an interaction was occurring at this time, at least, we should have some sign of it in somewhere, either in the light curve or in the spectrum. We don't see anything.
And it wasn't abnormally bright compared to.
Yes. To a sample of.
It was just normal.
Yes.
Is it located in a cluster of massive stars? Or is it isolated?
No. It is. No, it is isolated, I think.
Yeah, because it was like, oh no, that was the GKG, sorry.
No, yeah, that's
Yeah.
super exciting.
Yeah,
That's
that's
almost
pretty fun, so.
out of the galaxy. Yeah, sometimes I mix all of them. Yeah. So it's a puzzle.
Any other questions? If not, let's thank our speaker again. So they will be here for, like maybe 1 or 2 more hours today, and then and then they're going up to stuff tomorrow. So ask questions fast of them before they leave. All right, thank you for coming.